In 1926, a French farmer filed a patent for a device he claimed could triple crop yields. No chemicals, no machines, no fossil fuels, just a simple copper wire capturing energy from the sky. Official government records document the results. Grainy photographs showed 10-foot corn stalks and pumpkins the size of barrels. A British committee established under the Ministry of Agriculture spent nearly 2 decades investigating these claims, collecting evidence from experimental farms across Europe. Then the technology disappeared, almost overnight, as if systematically erased from agricultural history. Today, we're told that bigger harvests require more fertilizer, that healthy crops depend on chemicals purchased every season, that modern agriculture's dependency on synthetic inputs is inevitable, scientific, and irreplaceable. But what if we traded a fundamental law of physics for a bag of nitrogen? What if the free energy flowing through every garden on Earth could do what fertilizer does, without the subscription, without the soil depletion, without the environmental cost? This is the story of electroculture, a technology that worked so well it threatened a $1 trillion industry. A method so simple that suppressing it required academic dismissal, media silence, and the deliberate forgetting of what farmers once knew. The science is real. The patents exist. The modern validation is emerging. And the reason you've never heard of it reveals everything about who controls your food and why they need you dependent. Welcome to Veiled Earth, where we remember what they buried. The farmer who saw what others couldn't. Justin Christopholo was not a household name in science. He wasn't educated at prestigious universities or backed by research institutions. He was a farmer, an experimenter, and a relentless tinkerer born in rural France in 1865. By the early 1900s, while industrial agriculture was just beginning its transformation, Christopholo had become obsessed with a question no agronomist was asking. Could plants thrive not just on nutrients from soil, but on invisible energy from the sky? For decades, he poured his life into building strange devices. Metal rods, copper spirals, magnetic antennas staked into the earth at specific angles. His neighbors thought he'd lost his mind. But Christopholo was chasing something he'd seen with his own eyes, plants responding dramatically to electrical configurations that conventional science said shouldn't matter. On October 26, 1925, Christopholo filed patent number CH118648A in Switzerland. The document still exists in Swiss archives, publicly accessible to anyone who searches for it. It describes in precise technical detail an electromagnetic apparatus for terrestrial application, designed to capture atmospheric electricity and channel it directly into the Earth's surrounding plant roots. This wasn't folklore passed down through oral tradition. This was a legal patent granted by the Swiss government in May 1926. The specifications are clear. Copper plates arranged in specific configurations, magnetic steel components, precise orientations to magnetic north, deliberate grounding patterns. Christopholo didn't just patent the technology. He documented it. He published his findings in French agricultural journals. He invited anyone to visit his experimental gardens outside Paris. He provided photographs, yield measurements, and detailed construction diagrams. The images that circulated in European agricultural publications are genuinely unsettling. Cabbages taller than grown men. Pumpkins wider than wine barrels. Corn stalks reaching heights that defied every known growth pattern for the varieties planted. Were these photographs manipulated? Possibly. Early 20th century photography allowed for tricks. But the scale of documentation suggests something more systematic was happening. Multiple growers across multiple countries reported similar results using similar copper wire configurations. And then there's the British Electroculture Committee. The committee that investigated for 18 years. In 1918, the British Ministry of Agriculture established an official committee to investigate claims about electroculture. This wasn't a fringe group of enthusiasts. This was government-sanctioned scientific investigation. For nearly 2 decades, until 1936, the committee collected evidence. Field photographs, yield records, testimonials from inventors and farmers across Europe, technical specifications of various electrical configurations being tested. Their interim reports, many stamped, not for publication, catalogued everything from giant barley stalks to the peculiar devices sprouting in French and German experimental gardens. The committee's mandate was simple: separate fact from fantasy. What makes this significant is what they didn't do. They didn't immediately dismiss the claims. They didn't declare electroculture impossible based on existing theory. They investigated for 18 years, suggesting the evidence was compelling enough to warrant sustained attention from legitimate agricultural scientists. But here's what's strange. Despite nearly 2 decades of investigation, no definitive public report was ever released declaring electroculture conclusively proven or debunked. The committee's findings simply trailed off. By the late 1930s, references to electroculture disappeared from mainstream agricultural literature. The visual record remained. The patents remained. But the conversation ended before any final scientific verdict was reached. Understanding why requires understanding something most people never think about. The electrical field every plant on Earth already lives inside. The invisible ocean plants swim through. Every patch of open ground on Earth sits beneath an invisible river of electricity. This isn't mystical energy or pseudoscience. It's measurable physics documented in atmospheric science textbooks. The air above our heads holds a steady positive charge. The soil below holds a negative charge. Physicists call this the atmospheric potential gradient, and on a clear day it measures approximately 100 volts per meter of altitude. Think about what that means. If you could somehow stack meters vertically through the atmosphere, each meter would have a 100-volt difference from the one below it. This creates a constant electrical field flowing between sky and earth, always present, always active, regardless of weather conditions. It's not lightning. It's not something you can feel. It's a gentle, persistent voltage differential that has existed since Earth's atmosphere formed. And every plant on Earth grows directly inside this field. Plants aren't passive in this electrical environment. Their leaves and stems, covered in microscopic hairs, waxy surfaces, and cellular structures, act as natural conductors. Each blade of grass, each tomato plant, quietly collects electrical charge from the air surrounding it. Roots buried in earth connect to the negative pole of this planetary battery. The plant itself becomes a living antenna, a biological structure bridging the gap between sky and soil. This isn't metaphor. The electrical flow is measurable with simple instruments. Drive a copper rod into the ground, attach a sensitive voltmeter, and you'll register a faint but consistent current, proof that air and earth are continuously exchanging charge even on calm days. For most of human history, this background electrical field went unnoticed and unused. But in the early 20th century, experimenters like Cristofalo asked a revolutionary question. If every plant already functions as an antenna collecting atmospheric electricity, what happens when you give it a better antenna? The upgrade nature didn't know it needed. A copper wire is far more conductive than a plant stem. It collects charge more efficiently. It channels current more effectively. And when placed in soil with proper orientation to Earth's magnetic field, it can amplify the natural electrical environment that plants already depend on. The principle is elegantly simple: enhance what nature already provides. This is where electroculture diverges completely from chemical agriculture. Instead of force-feeding plants with synthetic nutrients they must metabolically process, the method aims to optimize the electrical systems that plants evolved over millions of years. The wire doesn't replace biology. It enhances it. It doesn't override natural processes. It amplifies them. But there's a deeper layer to this. Because electricity doesn't just flow through plants, it communicates information. The language plants speak electrically. Inside every plant, a constant conversation unfolds in the language of electricity. Roots, stems, and leaves don't just carry water and nutrients. They transmit electrical signals called action potentials and variation potentials that ripple through cells at speeds measurable in milliseconds. These aren't random fluctuations. They're information. When a tomato leaf is wounded, an electrical wave travels down the stem alerting distant cells to prepare defensive compounds. When roots encounter obstacles, electrical signals adjust growth patterns in real time. Plant physiologists have documented this for decades using fine electrodes that detect voltage changes at the cellular level. Even a faint external electrical field, just a few microvolts per meter, can trigger measurable responses. Gene activation, antioxidant production, growth rate changes. Some studies show that when exposed to optimized electrical gradients, plants ramp up production of compounds associated with stress resistance and vigor. The effect isn't limited to injury response. It can be triggered by environmental electrical conditions. This is where modern science begins catching up to what early experimenters observed but couldn't explain. Plants aren't just chemically responsive, they're electrically responsive, and that responsiveness can be deliberately influenced. Enter Drive, Philip Callahan. the USDA scientist who saw insects differently. In the 1960s and 70s, Dr. Philip Callahan worked deep inside the USDA's entomology labs. His official job was studying agricultural pests, but his background was unusual. He'd trained as a radio technician with the U.S. Army Air Force during World War II, mastering the detection of invisible electromagnetic signals. That wartime experience shaped the questions he brought into the lab decades later. Callahan began examining insect antennae under high-powered microscopes, searching for clues about how pests locate their targets. What he saw caught him off guard. The structure of moth and beetle antennae didn't look random or purely biological. They resembled finely tuned electromagnetic receivers, long repeating shafts covered in ridges and spines spaced at precise intervals. To Callahan, who understood radio engineering, this looked like deliberate design, like antennas built to detect specific frequencies. He published micrographs in technical bulletins, showing that insect antennae possessed geometric properties consistent with dielectric waveguides, structures capable of detecting infrared radiation and other electromagnetic signals beyond simple chemical detection. His radical hypothesis: insects weren't just sniffing the air for plant odors. They might be scanning for electromagnetic signatures, the energy field that healthy versus stressed plants emit differently. The signal only sick plants broadcast. Infrared cameras reveal something invisible to human eyes. When a plant thrives, its leaves release heat in a steady, uniform pattern, an unbroken field of thermal energy. Under stress, drought, disease, nutrient deficiency, that pattern fractures into chaotic patches of hot and cold spots. This isn't just temperature variation. According to Callahan's hypothesis, it's a signal. A healthy plant emits what he called coherent energy, a steady, high-frequency signature that blends into the background. Insects tuned to detect plant signatures can't distinguish it from environmental noise. The plant is effectively invisible. But when a plant weakens, its electromagnetic signature becomes chaotic, disordered, like a radio stuck between stations. To an insect with antennae capable of detecting infrared patterns, this is a beacon, a clear signal that the plant is vulnerable and ready to consume. Contemporary entomologists acknowledge that while chemical cues dominate insect behavior, some species, fire beetles, certain parasitic wasps, can detect subtle infrared shifts. The idea that insects decode complex electromagnetic patterns remains controversial, but the basic principle is documented. Stressed plants broadcast their distress in measurable ways. And if that signal is what attracts pests, then correcting the signal, restoring the plant's coherent energy field, could make the plant effectively invisible to insects. This is where a simple piece of copper starts looking less like gardening folklore and more like applied biophysics. The geometry that focuses energy, the spiral, became central to early electroculture designs. And there's a reason beyond aesthetics. Spirals appear throughout nature: snail shells, sunflower seed patterns, galaxy formations, because this geometry efficiently gathers energy from a wide area and focuses it to a central point. In Paris, 1923, Georges Lakhovsky demonstrated this principle with startling results. At the Jardin des Plantes, he worked with geraniums infected with crown gall tumors. No medicine, no chemical treatment, just a single loop of copper wire, open at one end, never a closed ring, slipped around the stem. Lakhovsky called it an oscillating circuit, inspired by the idea that every living cell vibrates at specific frequencies. According to his published accounts, the geraniums with copper coils survived and recovered while untreated plants died. The experiment was documented, photographed, and published. Lakhovsky filed patents describing the coil's exact design: a single open loop, always with a visible gap, never closed. Nearly a century later, that same design, the Lakhovsky coil, remains the foundation of modern electroculture practice. The geometry has barely changed since those first Parisian gardens. Why the open gap? Because a closed loop creates a short circuit. An open loop acts as an antenna, capable of receiving and resonating with external frequencies. The gap allows energy to flow in and out, creating oscillation rather than static conduction. This design principle, preserved in patent archives and passed through generations of experimenters, suggests something worked well enough to be worth preserving exactly. The industry that couldn't afford free energy. By the early 1920s, agriculture was about to be transformed by a chemical revolution, the Haber-Bosch process. invented during World War I to synthesize ammonia for explosives, was being repurposed for fertilizer production. Factories in Germany and the United States began producing synthetic nitrogen on an industrial scale. Production exploded from roughly 1 million tons annually in the 1920s to nearly 20 million tons by 1960. Prices dropped from $100 per ton to less than $30 per ton as economies of scale kicked in. But the real innovation wasn't chemical, it was economic. A new business model emerged. Farmers who once relied on compost, manure, or crop rotation now faced annual fertilizer purchases, buy chemicals every spring, or accept diminished yields. The subscription was built into the system. Each season, another purchase. Each year, another invoice. The fertilizer market transformed into a giant industry whose profits depended entirely on repeat sales. In this economic environment, a method that worked permanently with a one-time copper wire installation wasn't just an alternative technology, it was an existential threat. If electroculture worked as claimed, fertilizer sales would collapse, chemical dependency would end, the subscription model would break. The industry couldn't allow that possibility to be thoroughly investigated, not if it threatened quarterly earnings, not if it undermined the entire economic foundation being built. The silence that fell, the suppression wasn't dramatic. No burnings of books, no arrests, just silence. Newspaper coverage shifted. Headlines that once discussed electroculture experiments began using phrases like miracle claims and eccentric methods. Agricultural journals that had published electroculture studies went quiet. Manuscripts went unanswered. University researchers, dependent on funding from agricultural chemical companies, avoided the topic entirely. In influential academic circles, electroculture was quietly categorized as fringe science, a label that didn't require disproving the claims, just discrediting them socially. By the late 1930s, references to electroculture had been reduced to footnotes and folklore. The British Electroculture Committee's findings, despite 18 years of investigation, were never synthesized into a definitive public report. The conversation ended before the evidence could be fully examined, not because experiments failed, but because they succeeded in ways that were economically inconvenient. But the story didn't end there, because recently, something remarkable happened. The 3,600 hectares that changed everything. In recent years, researchers at the Chinese Academy of Agricultural Sciences conducted what may be the largest electroculture trial in history. The scope was staggering: 3,600 hectares. That's larger than 6,000 football fields. The setup used high-voltage wires suspended above crops, harnessing the natural electric field between sky and earth, the same atmospheric gradient that's always present. No synthetic fertilizer, no pesticides, just electrical current optimizing what plants already do naturally. The results were documented in institutional research published through official Chinese agricultural channels. Yields increased by nearly 30% across all crops tested: wheat, rice, vegetables. Everything showed significant gains without any chemical fertilizer inputs. Even more striking, pesticide use dropped by 70 to 100% in treated fields. Farmers reported dramatically fewer insects and healthier plants, even in regions where pest pressure had historically been severe. These weren't backyard experiments conducted by enthusiasts. This was institutional science at a national scale with sample sizes large enough to eliminate statistical noise. For the first time in nearly a century, the old claims, harvests multiplied by wire and natural voltage, had modern, peer-reviewed scientific backing. The technology that disappeared in the 1930s had been validated by one of the world's largest agricultural research institutions. How a copper spiral actually works. The method itself is almost absurdly simple. Take 14-gauge bare copper wire, the kind available at any hardware store. Form it into a loose spiral approximately 5 to 20 centimeters in diameter. 3 to 5 turns, spaced evenly. Use a wooden dowel as a form to keep the coil consistent. The finished spiral should have gaps allowing air and light through. It's not a solid mass, but an open structure. Drive a stake into the soil so the spiral sits 10 to 15 centimeters deep, with the top end pointing just above the surface. Critical detail: the tip must face magnetic north. Use a compass. This isn't superstition. Earth's electromagnetic currents flow along magnetic field lines oriented north-south. Alignment determines whether the system resonates with those currents or works against them. Position the coil 10 to 20 centimeters from the plant's base. Tomatoes, beans, squash, leafy greens, all respond to this configuration. To track results properly, measure baseline data before installation, plant height, leaf color and size, pest damage, take photographs. After 2 weeks, measure again. After 4 weeks, compare. One Ohio gardener documented a 40% increase in lettuce yield using 1 copper spiral per row. Same soil, same water, same sun exposure. The only variable, 1 piece of wire. The experiment costs less than $5. It requires no external electricity, just the atmospheric potential gradient that's always present. And it's completely safe. No shock hazard, no chemical exposure, no environmental risk. For anyone willing to test it, the method is accessible, replicable, and potentially transformative. The pesticide treadmill they won't explain. The global pesticide market generates over $60 billion annually. This isn't a side business. It's a financial engine that depends on farmers and gardeners returning season after season for another round of chemicals. And here's the mechanism that keeps it running. Pesticides don't just kill insects. They stress the plant. Chemical sprays damage cellular structures. They lower internal electrical potential. They weaken the plant's natural defense systems. And that stress changes the plant's electromagnetic signature, making it more attractive to the next wave of pests. This isn't conspiracy theory. Agricultural extension bulletins quietly acknowledge this cycle. Each pesticide application reduces plant resilience. As immunity drops, the plant broadcasts a stronger distress signal, whether through volatile organic compounds, weakened cell walls, or altered electromagnetic fields. More pests arrive, drawn to the easy target. The solution, according to the industry, is always more product, a new formula, a stronger dose, the latest chemical blend. This is the pesticide treadmill, and it's enormously profitable. Spray to kill pests. Spray stresses plant. Stressed plant signals vulnerability. More pests arrive. Repeat. The system doesn't reward healthy plants. It profits from sick ones. The more you fight, the more you buy. And if a simple copper wire could break that cycle by restoring the plant's coherent energy field, making it electromagnetically invisible to pests, the entire treadmill stops. That's not a product line extension. That's industry collapse. Why they can't let you remember. Today, global fertilizer use exceeds 185 million tons annually. Soil health continues declining. Input costs keep rising. And farmers remain locked in a cycle of dependency that previous generations never knew. The real question isn't whether electroculture works everywhere under all conditions. The question is why simple, low-cost experiments that threaten billion-dollar industries remain buried in patent archives and forgotten journals. The evidence exists. The patents are publicly accessible. The modern validation is emerging from institutional research. And the method is simple enough for anyone to test in their own garden. But you've probably never heard of it. Because when free energy meets corporate resistance, information doesn't flow freely, progress doesn't happen naturally, and technologies that threaten quarterly earnings don't get fair investigation. They get categorized as fringe, dismissed as pseudoscience, and quietly erased from mainstream discussion. Justin Christopholo spent decades documenting his results, filed legal patents, and invited public scrutiny. The British Electroculture Committee investigated for 18 years. George Lukoski demonstrated his coils in public gardens. Dr. Philip Callahan published his findings in USDA bulletins. None of them were charlatans. They were serious experimenters producing results that didn't fit the economic model being built around chemical agriculture. And that's exactly why the technology disappeared. Because a copper wire that works for 20 years can't compete with a fertilizer bag that must be purchased every spring. A one-time installation can't generate recurring revenue. And a method that makes farmers independent can't sustain an industry built on dependence. What you can do right now, the technology isn't lost, it's just buried. And anyone with $5 in a hardware store can test whether the claims hold up. Take copper wire, form a spiral, orient it to magnetic north, place it near a plant, measure the results. If it works, you'll know within a month. If it doesn't, you've lost less than the cost of a bag of fertilizer. But if even a fraction of the historical claims prove true, if plants really do respond to optimized electrical fields, if pests really do avoid electromagnetically healthy plants, if yields really do increase without chemical inputs, then this simple experiment becomes something larger. It becomes proof that the system lied, that dependency was manufactured, that the solutions we need have been available all along, just hidden beneath layers of economic interest and academic dismissal. The harvest of the future doesn't depend on new technology. It depends on remembering what we were taught to forget. This is Veiled Earth, where we dig up what they buried. If this story made you question what else you've been told about growing food, subscribe. Share this with someone who still believes industrial agriculture is the only way forward. Because every person who plants a copper wire and measures the results becomes a little harder to control. Every garden that thrives without chemicals is proof the subscription wasn't necessary. The technology exists. The patents are public. The science is documented. All that's missing is people willing to remember. What will your harvest prove?